Okay, so now let's see some examples of how to calculate uh, the sample size with G-power in this case. Okay, so let's first I have taken the examples from this book, Statistical Design for Animal Research, that I wrote a number of years ago. And here is the link to the book, and also here you see the outline of the first chapter. Actually, the first and the fourth chapter, they are very useful for anyone working in experimental uh, uh, in experiments with research animals and having to analyze the data coming out from it. So if you are interested, I recommend you to read these couple of chapters, and the chapters 2 and 3. The first one is related to sample size. The second one is related to experiment design. Okay, so let's see an example. So we let us assume that we are studying the effect of a new compound A on the intraocular pressure of a mouse strain that serves as a model of glaucoma. So glaucoma is a high pressure within the eye. So the compound is administered in eye drops so that one eye of the mouse can be given the new compound, while the other one may serve as its control with only the vehicle being administered. Since an animal serves as its own control, we reduce the variability between subjects, and the effect of the treatment is easier to detect due to the lower variance. Remind when we were talking about the variability of observations, we had biological variability plus the noise of measurement noise. So the biological variability between different animals, because they are different individuals, they will have a larger variability. But if you use the same animals as its control, then much of this variability, genotypic, phenotypic variability, is eliminated. So let us assume that the intraocular pressure without treatment is about 14.8 millimeters of mercury, and with a standard deviation of about 2.2. And we want to detect pressure, so this is the noise, and we want to detect pressure reductions of 0.5 millimeters of mercury. So this is the gap that we want to detect. This is the effect size. And let us assume that the standard deviation with and without treatment is the same. Okay, so let's see how to do that. So let me call to G-power. So just to have the two windows together, let's make this smaller. So we can have a G-power on one side and the other one in here. So we want to make a test. Okay, so it is a test. We are comparing means. So we are comparing means. Now we have multiple choices. So we have one group. So we are comparing the mean of a group to a constant, and we can make that comparison non-parametric. So actually we have all the time this choice of non-parametric or parametric comparisons. So we don't have a group, we have two groups. So we have two independent or dependent. So independent groups, the animals are different in each one of the groups, but in our case, we have two groups, but the animal is the same. So we have measurements before or left eye and right eye. You can also do that for before and after treatment. We don't have many groups. We don't have repeated measures. Repeated measures is when you apply the treatment once and then you measure at multiple times, like at 0 time equals 0 time equals 24 hours, 48 hours, and so on. So we are here, two dependent groups match pairs. So we have pair samples. this is the same. And we will have the two possibilities, parametric comparison, that is a t-student, or a non-parametric. So the t-student assumes that the data is distributed Gaussianly, so you have a normal distribution of the data. So let's go for this one. And now here we can compute the sample size given alpha, given the power, and given the effect size. And it is implicit there, but it is also the noise. So the amount of noise that we have. So here we see these 5 variables that we were talking before. So given 4, you can calculate the 5th one. So here we are calculating the sample size. Here we are calculating alpha. This is power. So this is beta. This is the effect size. And this is how a combination of alpha and power. But it is given 4, you can calculate the 5th one. Okay, so let's go for the calculation of the sample size. And now it comes how many tails you will use in your comparison. So we can have two possibilities. So one is we want to detect, we will use an eye drop, and this eye drop may increase the pressure or may decrease it. But if we are interested only on one side, I don't want to find those drops that increases the eye pressure. So I only interested in those that decrease it. So that is a one tail. If I'm interested in both, any drop that makes a change in the eye pressure, then it is a two tails, because I don't know if it will increase or decrease, and I want to detect both. So that is a two tails. While if you're interested in only detecting those that decreases, that is a one tail, and it has an impact on the sample size. Okay, so now it is asking for the normalized sample size, but we don't know how to normalize them. So let's use this calculator to calculate this normalized sample size. So let's say that this is 14.8, is control the pressure in the control group, and we want to detect a change of 0.5. So we want to go 14.3. The standard deviation of the two is 2.2, 2.2. Okay, so now correlation between groups. So even if it is the same animal, the two eyes may not have the same intraocular pressure. So let's say that this animal has developed glaucoma, but the pressure in one eye is not correlated at all with the pressure in the other eye. So that would mean that the correlation between the two is 0. But this is quite weird. So we would expect not to have exactly the same value, but probably to have a value that is rather similar to between the two eyes. So let's say that this is 0.9. Okay, so now we calculate the effect size. So the effect size is we want to detect something that is 0.5 and in a level of noise that is of the order of 2.2. So we will see it later if we will design these with independent groups. So independent groups would mean having independent animals. So you would apply the eye drop to the treatment to a set of animals, and you would measure the glaucoma in some other set of animals that are untreated, and then you would try to determine whether there is a difference between the treated and the untreated animals. Okay, so this effect size, the formula to calculate this is complicated, but we see that we have to detect something that is this big, and if there is no correlation, for instance, then it is much smaller. So yeah, so it is easier to detect a change when the two eyes are correlated than when the two eyes are uncorrelated. So because we expect the data to be correlated, so we can use this 0.9. Okay, so now we calculate the normalized effect size, transfer it to the main window, and here we have the probability of having false positives, the probability of making false negatives, and we can calculate this sample size. So we will need 44 animals that will give us 43 degrees of freedom, and there is a critical T that is 1.68. So we will calculate, we will perform our experiment. We will calculate the T, that there are formulas for that. If the T that we calculate is beyond 1.68, we would reject the null hypothesis. And this will make false positives with probability 0.05, and we will make false negatives with probability also 0.05. It is this one, when the change is 14.3, so the change is 0.5. So we will detect changes of 0.5 with a power of 0.95. Okay, so yeah, so two tails. Let's say that we want to detect either increases or decreases of the eye pressure. Now it is 53. So we have increased from 44 to 53. So that is 9 more animals. That is I don't know, about 20% of more animals. And now we will have a critical T that is different, and we will have on this side alpha half, on this side alpha half. So you see that choosing whether you want one tail or two tails makes a difference in the number of animals. You can increase or decrease the number of animals by as much as 20% simply by choosing the right statistical test. So you are interested in the case of glaucoma, you are interested only in those compounds that decreases the intraocular pressure. You're not interested in detecting whether it increases or not. So one tail can save rather a lot of animals, so 20% of animals. So again, be very careful about the way you design your experiments, because that has an impact on the number of animals that at the end, well, we have to take care of them and make sure that we don't use more than we need. And that is one thing. Let's say that we don't know of these paired, we don't think of these paired samples, and we have two groups, one that is untreated, the other one that is treated. All animals are originally the same, but we will treat some and not the others. So here we have 44. So let's see how the sample size changes. Now let's say that our two groups are independent. So now I know that I have to use only one tail. So this is 14.8. This is 14.3. The standard deviation here is 2.2. The standard deviation here is 2.2. So now I have to detect. So I want to detect something that is 0.22 the level of noise. So before it was 0.5. So I wanted to detect something that was half size the level of noise. Now it is a quarter of the level of noise. So it is a smaller signal that I want to detect. So I should expect more animals in that I need more animals. It is not that I need more animals, I need so many more. So before to detect this change with single set of animals, I only needed 44 animals. Now I need 800 animals. So that means probably, okay, you cannot be with two independent groups, you cannot be as precise as to detect just such a small change. So there are several lessons here. So if you can use paired samples, that save a lot of animals. The other one is if you want to be very precise, you will need a lot of animals. So I cannot use so many animals. So let's say that I want to use as many as before, that there were 44 in total. So 44 in total, it is 22 per group. Okay, so let's see. I will have to decrease my sensibility. So my sensibility, let's see. Okay, so still I have too many. So 64, 68. So let's say this is 2.5. Yeah, now, so almost 44. So either I see a big change, 2.3 from one to the other. So that is one standard deviation, or with two independent groups, I will not be able to detect this change with a power that is 0.95. Does it mean that I cannot detect smaller changes? No, you can, but with a smaller sample size. So with a smaller power. So we can, what is the power? So what is the power? So let's say we had before these, so for instance, can I not detect changes that are smaller? So now we can calculate this one, this will keep fixed to 21 per group, and yeah, you will detect it, but now with a smaller power. So the smaller the gap, the smaller the power you have to detect that gap given a fixed sample size. Let's say that my difference is as small as it was before. So now with only 21, I have only this probability of detecting it. So only in 17.8% of the cases, I will be able to detect this change. And yeah, so yeah, that is all I think that, no, that there is another important thing here. So let's say that let's go back to the sample size. So yeah, let's make this more detectable. So we say something like this. So we need only 21 animals per group. So let's say that one of the groups is much more difficult to handle than, or to find, than one of the other groups. So this is not the case in this case of glaucoma, but let's say that you are working with rare diseases, and controls you can have as many as you like, because healthy patients or yeah, healthy people you have as many as you like, but people with a particular rare disease, they are much more difficult to find. So you can say, okay, one of the groups will have, let's say, a tenth of the size of the other one. So you can say one of the groups will be 10 times smaller. So now you can have a group with as few as 11, and the other group, again, there is no free lunch. So the statistical tool allows you to have different group sizes, but if one decreases almost by a factor 2, the other one has to increase a lot to have the same power to detect this change. But it is doable. So that means that you can have a lot of healthy people, and you apply your treatment to these healthy people and to the people with the rare disease. So you don't need to have balance in these sample sizes. Let's go for the next case, and we will not cover all of them that I have prepared here. For small proportions, yeah. So for small proportions, so let's say that you are developing a vaccine against a pathogen. So you are interested in vaccines for which the probability of infection when directly exposed to the pathogen is only 1%. How many individuals do you need to show that a given vaccine is useful? So now your problem is not a problem about means. It is a problem about proportions. Okay, and it is, do you have two groups or one group? No, we have only one group. So we have one group difference from constant. Okay, so we have a difference from this 1%. Okay, now, what is the probability in one of the, so what is the gap that you want to detect? And again, this comes to how to answer the different questions of the form. So it is not easy. So in the sense that it is what is the gap for which you want to have a given power. So let's say that it goes from 1%, it goes down to 0.005. So yeah, I think I can calculate the odds ratio. The odds ratio is yeah, it is, again, it is a little bit complicated, but you can think of it as a ratio between P1 and P2. It is not exactly that, but yeah, that is why we don't get 0.5 exactly. But okay, so we calculate this. We calculate this one, transfer to the main window, and this is the alpha that we want to have. This is the power, and this is the constant proportion. This is the constant here that we want to have. Okay, so we want to compute the sample size. Again, we have the 5 possibilities. We calculate how you need 3,000 individuals. Why so many? Because it is a very rare event. So it is very rare, so that most of the cases, so let's say in 3,000, you expect, you expect 30 of them only to be infected. So if it is smaller than that, so if it is smaller than 22, this is our now critical value, then you would say that your vaccine is successful. So, and this would be all, and see you in the next video, where we will draw some conclusions.